class we will continue the calculation of packing efficiency for different unit cell, okay, cubic unit cells. We have already discussed about the FCC. So in this class we are going to discuss about mainly about the body centered cubic structure and the that means the primitive cubic unit cell, okay, just a simple or primitive unit cell. So let us discuss one by one. Okay. So first we are going to discuss about the BBC, that means the body centered cubic structure, okay. So for that we need a that unit cell. So let's suppose this is your body centered unit cell, okay. So it is taken from your NCERT book, okay. So here we know that the packing efficiency is equal to volume of the spheres, okay, inside the unit cell divided by the total volume of the unit cell, okay. So we have to multiply this by 100% to convert it percentage, okay. So this is the definition of packing efficiency. So here you see we need the volume of the sphere inside the unit cell and the total volume of the unit cell, okay. So we have the unit cell, the figure of the unit cell, and we have the formula. So now what we have to do, we have to use this formula and this figure to calculate the packing efficiency, okay. Let us first calculate the volume of spheres inside the unit cell, okay. We know that again we know that the number of spheres, or you can say atoms, okay, atoms present in the BCC lattice is what is equal to 2. So we have already discussed about this calculation of number of atoms present in different unit cells, okay, in previous class. So if you don't go through that video, then please go through that video, okay. So now we have the number. So we know that the volume of spheres is equal to 4/3 pi r cube if r is the radius of that sphere, okay. So let us suppose that radius of all the sphere, that means all the atoms are smaller, okay. So we can write the volume of the sphere is 4/3 pi r cube, okay. But how many atoms are present inside that BCC unit cell? So 2, number is 2, okay. So that means the total volume, that means volume of 2 spheres, okay, 2 spheres inside the unit cell is equal to 2 into 4/3 pi r cube, okay. So we have this we able to get the volume of the 2 spheres inside the unit cell. That means this part is done, okay, this part is done. So up to now we have the volume of the spheres inside that unit cell, okay, which is actually 2 into 4/3 pi r cube, okay. So now we will calculate the total volume of the unit cell. So the total volume of the unit cell. So now we will calculate the total volume of the unit cell, okay. So for that actually we have to concentrate on this figure, okay, this body centered cubic unit cell. So from this figure it is evident that the atom at the center will be in touch with the other 2 atoms which are actually at capital A and capital F, okay. So this center atom will going to actually touch with the atom A and F diagonally. Okay, so let us suppose the body diagonal, which is represented by FA. Okay, so suppose the body diagonal which is actually what? FA is equal to small c. Okay, so that means the length of the body diagonal is equal to small c, and the face diagonal, let's suppose the face diagonal FD. Okay, FD is equal to small b. Okay, small b. So small c and small b. So we have this data now. So now we're going to use this data, and its length is equal to A. So edge length means the length of ED, B is equal to B, CD is equal to CF. All the edges are equal to A. Okay, because we already know that the length of the edges are equal. Okay, so the total volume of the unit cell will be actually A cube if the edge length is A. Okay, because the lengths are equal, all the edge lengths are equal, so the volume is equal to the A cube. Okay, so we have this volume, but what we have to do here, you see we have the volume of the two spheres which are present inside that unit cell is in the form of what? R, small r. So we have to we have to actually express this volume in terms of R, where R is what? R is actually the radius of the spheres. Okay, so for that, let us suppose if you consider the triangle here, if you consider the triangle EFD. Okay, so in case of EFD, you see EFD is actually right angle triangle. Okay, so in triangle EFD, so this triangle is right angle triangle because here angle DEF is equal to 90 degrees. So we can use what? Pythagoras theorem. So by using the Pythagoras theorem, you see the B square is equal to A square plus A square. Actually B here, this B is coming from what? FD. Okay, and this A is coming from ED, and this A is coming from EF. Okay, understand? So simple mathematics. So this will be equal to B is equal to root over 2A. Okay, so we have this value also. So that means we have this value of the face diagonal. So now let us calculate the value of the C. That means the body diagonal. Okay, so we can calculate the body diagonal from from the triangle AFD. So if you look at the triangle AFD, then you see here it is actually in this triangle also the angle angle ADF is equal to 90 degrees. That means it is a what? Right angle triangle. So we can again use Pythagoras theorem. So by using the Pythagoras theorem, we can say that AF square is equal to AD square plus DF square. Okay, so in place of AF square, what we can write? C square is equal to what? AD square. AD square in place of AD square, it will be what? AD square is equal to A square. Okay, understand? Plus in case of DF square, we have to write B square. Understand? So here you see we have the value of B is equal to root over 2A. Okay, so we can put this value here. So it will going to give you C square is equal to A square. Same, in place of B square it will be plus 2A square. So is equal to 3A square, or we can write what? C is equal to root over 3A. Understand? So if you look at this the definition of packing efficiency, then you see in the the numerator, the volume of the spheres present in the unit cells are in terms of small r. That means the radius of that sphere. Okay, but here we have the value of this a, that's a cube, okay. So that means the denominator we have the value r in terms of a cube, okay. So to cancel out this numerator by the denominator value, okay, that means we have to convert this denominator also in terms of, we have to actually express this denominator in terms of small r, such that we can cancel out the term r, okay, to get the only numerical value, okay. So here we have the c is equal to root over 3a, okay, but here we can write the value of a in terms of c only by using this relation, okay, but we need to actually express the a cube, that means here a cube, okay, in terms of r, understand. So for that, what we have to do, we have to convert this c in terms of smaller. So for that, we again have to go to the figure. You see this figure, if you look at this figure, then you able to see that actually the value of c, this value of c is equal to, that means the body diagonal, that means the length of this body diagonal is equal to actually r, okay, plus 2r plus r, okay. So it will be your 4r. So in place of this c, we can write 4r. So c is equal to 4r is equal to root over 3a. So we can easily write a is equal to what? 4 by root over 3, 4 by root over 3r. So that means we can place this value, or we can put this value of a here in a cube to get the total volume of the unit cell in terms of r. So that means the total volume of the unit cell is equal to a cube is equal to what? 4 by 3, 4 by root over 3 r cube. Understand? Actually, if you try to summarize the things, actually how to calculate the packing efficiency, actually we have to use this formula, no doubt, okay. So in case of the volume of the spheres, we have to write the volume of the spheres present in the unit cell in terms of r, that means the radius of the sphere, okay. So also we have to write the total volume of the unit cell in terms of r, actually to cancel out the r, such that we will get the value in terms of only numerical value, that means no any variables, understand. So now let us put the value of the volume of the spheres present in the unit cells and also the total volume of the unit cell in this equation, okay. So the packing efficiency, so the packing efficiency is equal to packing efficiency of body centered cubic lattice, that means BCC, is equal to what? So in place of volume of the sphere, we can write here 2 into 4 by 3 pi r cube, and in place of this a cube, so that means the total volume of the unit cell, we can write 4 by root over 3, okay, r cube. So it will be equal to 8 by 3 pi r cube, so this will be in bracket, okay, into 100% divided by 4 into 4, 16 into 4 is 64, okay, 64 divided by divided by, you can write here that this 3, okay, 3 root over 3 r cube, okay. So actually if you calculate this this mathematical problem by using a calculator, then you will get 68%, okay, almost 68%. So that means the packing efficiency of the BCC unit cell is 68%, and the physical significance of this is that only 68% of this cube is occupied by the spheres present inside that unit cell, and the remaining part will be empty space, or it will be in the form of some voids. Understand? So let us now calculate the packing efficiency for simple cubic unit cell or primitive cubic unit cell. Okay, for that we need obviously we need that unit cell, that means primitive unit cell. Let us suppose this is the primitive unit cell. Okay, so we already know that in case of primitive or simple cubic unit cell, all the corners are only occupied by the the spheres or the constituent particles or atoms. Okay, so here the 8 corners are occupied by 8 atoms. Okay, and all the atoms are touch with each other along the edges. Okay, so if you look at this figure, then you able to find out that the value of the edges. So let's suppose, first of all, let's suppose the edge length of the unit cell is equal to A. Okay, so as before, we just suppose that the length of the edge for this unit cell is small a. Okay, so and the radius of the spheres or atoms, you can say atoms, is equal to smaller. Understand? So if you look at this figure, then here you see, because they touch with each other, so the value of A is equal to actually 2R. Clear? Again, we know that the packing efficiency, so I'm just writing P. Okay, but in exam please write the full form. Packing efficiency is equal to actually what? The volume of the atoms or sphere present in that unit cell. So here we can write what? The volume occupied by the spheres, by the atoms or spheres. We can spheres. Okay, spheres present in that unit cell. Okay, so right here, present in that unit cell divided by total volume of the unit cell. Okay, of the unit cell. Okay, so here here we have to write what? Total volume of the unit cell. So here it will be the total volume of unit cell is equal to what? Volume of the unit cell is equal to A cube. So here in place of A we can write A cube by using this formula. A cube is equal to what? 2R cube is equal to 8R cube. So in the numerator we have the volume occupied by the spheres. So how many spheres or atoms are present in case of primitive cubic unit cell? We know that it is 1. Okay, so we have to write the volume occupied by the 1 sphere. Okay, so it will be very easy. Okay, so that means we know that the volume occupied by 1 sphere is equal to 4 by 3 pi R cube. If the R is what? R represent the radius of the atoms or the spheres. So here in place of total volume of the unit cell, what we can write? 8 R cube. So R cube cancel. So here we have to write the 100% and also here 100%. So here 100%. So if you calculate this one, you will get the value as 52 point something. Okay, 52.36%, or you can almost write it is almost equal to 52.4%. Understand? So we can conclude that only 52.4% of that unit cell is occupied by the atoms, and the remaining part of that cube will be remaining as a void. Okay, understand? So if you compare all the 3 unit cells, that means FCC, okay, that means FCC, okay, and BCC, and that primitive cubic unit cell. Okay, primitive cubic unit cell. So if you compare these 3, then you are able to see here that this, in case of FCC it is 74%, in case of BCC it is 68%, and in case of primitive cubic unit cell it is 52.4%. That means the FCC is the more efficient, the packing efficiency is highest in case of FCC. That means, and the lowest in case of primitive cubic unit cell. Okay, so that means the highest void in case of primitive cubic unit cell, lowest voids in case of FCC. Hope you understand this, calculation of packing efficiencies for different types of unit cells, and these calculations are very important for your exam. Okay.